Welcome to this video. We'll be walking through the modeling physics of OCR Physics A, and this is the May/June 2025 series. Let's get started with section A. In the first question, we've been asked which of the physical constants require the greatest number of different base SI units. So for A, which is the Avogadro's constant, the unit is simply per mole, so that's out. Boltzmann constant, we know it is given by joules per Kelvin, which if I wanted to split up is going to be kilograms meter squared per second squared per Kelvin. Then we have gravitational constant, which has units of newtons meter squared per kilogram squared. Okay, so that can be further split up into kilograms meters per second squared, meter squared, and kilograms to the -2. Finally, we have molar gas constant, which is joules per mole per Kelvin. So that will be kilograms meters squared per second squared, mole per moles, and then per Kelvin. So in the last one, we have the most different base units. D is the answer. Question 2. A metal block of mass M is at a temperature of T0 and an electrical heater of constant power P heats the block for time T as it reaches a temperature of T1. The overall efficiency of this process is X, which is the correct expression for the specific heat capacity of the block. So we know C is equal to E, the energy transferred, divided by M delta T, which is just a change in temperature. So because this system is X amount efficient, you're going to have X amount of the total energy being transferred, which can therefore be written as X times P times T, which is the time. So that will give me C as the correct option here. Let's move on to question number 3. Which row of the table describes the conditions which apply to an inelastic collision? We know that the kinetic energy is not conserved. Total energy and the momentum are conserved. So that would give me B as the answer. Then question number 4. A light rod is hung from a horizontal ceiling using 2 springs, one attached to each end, and the springs have force constants K and 2K. And a downward force F is applied closer to one end of the rod such that the rod is horizontal. And they're asking us the tension in the spring with force constant 2K. There are 2 ways of looking at this question. One is based on the spring constant. So we know that this is with a force constant 2K, which means that this is stiffer. Okay, this side is stiffer, and that means that it would stretch less for the same amount of force. Okay, and the force is shared between the two. So that means the tension must be greater. Okay, so it can't be B or D. A is 1/3 F and C is 2/3 F. 2/3 is greater than 1/3, so C would be the answer. Okay, one way of looking at it. The other way is more mathematical. We know the length of the rod was L units, okay, and this is split up into, let's say, 1:2 ratio. Okay, it's obviously closer to the left-hand side. Okay, and so if we look at the equilibrium, given that this is in equilibrium, when we look at moments about this side, okay, we take this as a pivot and talk about the tension. Tension is acting at a distance of L, and the force at a distance of 2/3 of L. Okay, so tension will therefore be, again, 2/3 of F. So That is the moment's way of looking at it, but I prefer the first, more logical answer. So let's move on to question number 5, where it says a material is heated so that it changes state from solid to a liquid, and after further heating changes to gas. Which properties of the particles have increased? Mean kinetic energy, order, and spacing. Okay, so we know that although when it's changing the state, there is no change in kinetic energy, we are given that it's heated further, which means that the mean kinetic energy would still increase during this further heating. Number 2, order. As it goes from a solid to a liquid to a gas, the particles become more disordered. For anyone who takes chemistry A levels, you would understand this as the entropy of the system increases. That is not true. And number 3 is spacing. Of course, the spacing increases. So our correct answer will be A over here. So watch out, because order can be sometimes confusing. It's the disorderness that increases. Okay, question number 6. We are given that a small particle of mass m is traveling horizontally between two parallel walls with a velocity v, and the weight of the particle is equal to the thrust caused by the air. The distance between the walls is L, and the effect of drag is negligible. Okay. After colliding with the wall, particle rebounds with a velocity of equal magnitude and travels in the opposite direction, hitting the opposite wall. The motion continues. And which row in the table is correct? Change in momentum is equal to m times delta v. And because the magnitude is the same and it's opposite direction, so when it hits it, it goes like this. Okay, so it'll be negative v. The overall change will be the sum of the two momenta. So you would have either B, C, or D for that reason. And then for the time between collisions, it's going L meters forward and back the same amount. So the total distance traveled, if V is equal to distance divided by time, it's going to be 2L over T. Therefore, T is 2L over V, so that gives me either B or D. Now, for the average force exerted on the wall, we have to think about F equals change in momentum over change in time. So we know that change in momentum is 2mv, and the change in time is 2L over V. So that becomes essentially 2mv squared, or rather just the 2 cancels out, so mv squared over L, for which B stands true. Let's move on to question 7. The apparent position of a star changes by an angle of 10 to the minus 4 degrees between observations made 6 months apart from the same place on Earth. What is the distance of the star from Earth in parsecs? Okay, so let's just imagine that you have basically the sun over here and the Earth here, and 6 months later it's over here. The distance between Earth and the sun is 1 AU, and then we have the star over here, and we are given that the angle that it makes in these 6 months is 10 to the minus 4 degrees. We have to remember that D is equal to 1 over P. 1 degree is 3,600 arc seconds. 10 to the minus 4 degrees is 0.36 arc seconds. As theta is 0.18 arc seconds because it is halved, D is 1 over 0.18, which gives me B as the answer. Okay, question number 8. A washing machine with a circular drum of diameter 0.6 meters is rotating at an angular velocity of 15 radians per second. What is the magnitude of the force exerted by the drum on a 0.3 kilograms item of clothing which is at the bottom of the spinning drum? Let's draw this drum. We've got this 0.3 kilograms, so 0.3 g newtons of force, and we have this force, normal force, and we are given the diameter is 0.6 meters. So the centripetal force is the overall force here equal to the normal reaction force minus the weight of this object or this item, which is 0.3 g newtons. So if you want to work out the value of this N, that will be equal to the centripetal force. I'm going to use m omega squared r here as I'm given angular velocity. Then add 0.3 g and you will end up getting a very easy answer, which is B. Okay, so remember it's the net force that you're looking at, and that is the centripetal force, the resultant force, and that is equal to the reaction force minus the weight of the item. So that is going to be 23 newtons or B. Okay, question number 9. Two spheres of radius 10 meters and mass 1600 kilograms exert a gravitational force of 1.7 times 10 to the minus 8 newtons on each other. What is the shortest distance between the surfaces of the spheres? Let's draw this out. You have this sphere and an identical sphere at a certain distance apart. We don't know that distance, but for gravitational force, it's always the distance from the center. So this is R and this is R. I'm going to call this distance D, okay, meters apart. F is equal to, ignoring the negative sign, G m1 m2 over R squared in general. But keeping in mind the radius of 10 meters for each sphere, you're going to have 20 plus D squared. And it becomes reasonable to work this out. So 20 plus D is equal to the square root of G m1 m2 over F, and so that is 80 meters. Question number 10. Which determines whether a super red giant evolves to a black hole? It's the mass of the core, so C is the answer. Question number 11. We've been given monochromatic light of wavelength 600 nanometers passed through a diffraction grating. Maxima are formed on a screen 3 meters from the grating, and the distance between two first order maxima on either sides of the zero maxima is 1.42. So all they mean is that you have the center maxima and you have the first order maximas. So this distance over here is 1.42 meters. So they're asking us to work out the spacing in the diffraction grating. So we know we have to work out D, and we know n lambda is equal to d sine theta. So we have to work out the value of theta given a bit of trig. Okay, so we know that this is going to be angle theta over here, and this distance over here is 3 meters, and this distance is 0.71 meters, and so theta is equal to tan inverse of 0.71 over 3, which gives me 13.3 degrees. Then d is equal to n lambda over sine theta, and we know that n is 1, lambda is 600 nanometers, so 600 times 10 to the minus 9 over sine of 13.3 degrees, which will give me D as the answer. Okay, question 12. Which option gives the likely evolution of the Sun? Sun will follow red giants, and then it will join the category of dwarfs. So B will be the answer here. Okay. Question number 13. We are given the surface temperature of the Sun, which is 5800 kelvins, and the peak wavelength is 500 nanometers. What is the surface temperature in kelvins of the star represented by the graph below? So a question like this came up in 2024 paper, I believe, and it was a very long question, and it required you to compare Wien's law of the Sun and the star. So hopefully people who have done the 2024 paper remember this question. We know lambda max is inversely proportional to 1 over T, which is the temperature in kelvins. So we can, in order to work out the surface temperature of the star, we use ratios, and we can say that T of star is over T of Sun is equal to lambda of the Sun over the lambda star. We need to work out the peak wavelength. Okay, so that would be somewhere around, I would say, 430 nanometers. So the value of T for the star is going to be lambda of the Sun, which is 500, times by the temperature of the Sun, which is 5800, divided by lambda of the star, which is 430, roughly. And that gives me approximately 6400 kelvins, and so C is the answer. Let's move on to question 14. A body moves with simple harmonic motion. Which graph shows the correct relationship between its time period and its amplitude? Time period and amplitude are independent. D is my option here. Time period depends on the dimensions or the length of the string. Question 15. Which of these statements above about the universe is implied by cosmological principle? According to this principle, the universe is homogeneous and isotropic on large scale. So that means that all the physics laws apply anywhere and everywhere. So Kepler's law can be applied to any solar system, hence B is my answer. Let's move on to section B with question 16. We're given that an electric car of mass 1700 kilograms is tested to measure its maximum speed. And figure 16.1 shows a graph of velocity against time for the first 18 seconds of the test. During this time, the force produced by the motor is constant, and we got to describe, using figure 16.1, the method you would use to estimate the distance traveled in 18 seconds. So because this is a velocity time graph, it would be the area under the graph that will give me the distance traveled. And in order to work out the area, I would look at the little sections. Okay, so for example, I would have to think about drawing triangles and perhaps a few trapezia. Okay, and this will be an estimate. It's not asking us to calculate the value, it's just asking how you would work it out. So it would be the area under the curve. You would measure or calculate the areas under the triangles and trapezia by calculating. So for example, you know that if you want to calculate any excess of the boxes, the small squares, that you would have to worry about, like working out one tiny little square as well, okay, adding them all up basically. Thank God we do not have to actually calculate them. Let's move on to part II. Using the graph, we need to show that the acceleration of the car at 12 seconds is about 1.5 meters per second. We know acceleration is the gradient. I have drawn a line at 12 seconds, so I need to draw a tangent. The gradient of this tangent will be the acceleration at 12 seconds. At t equals 12 seconds, the acceleration is the gradient, which is 60 minus 34 divided by the change in time, 15.6 minus 0. That gives me 1.6 meters per second squared. The acceptable range is between 1.4 to 1.7. So that's fine. Let's move on to our next question. Use figure 16.1 to calculate the change in momentum for the car in 18 seconds. So we know that change in momentum is mass times change in velocity. We need to consider the maximum velocity, which is 56 meters per second. The mass of the vehicle is 1700, so it'll be 1700 times 56, or 95,200. I am going to round that to two significant figures. Let's move on to part B. Figure 16.2 shows a graph of resultant force against time during the test. Explain in terms of forces acting on the car the shape of the graph in figure 16.2. As the car accelerates to a maximum constant speed of 56 meters per second, the resistive forces begin to increase. And this causes resultant force, which is equal to the driving force minus the resistive force, to decrease to 0. Part II. Explain why the value you calculated in part A is the area under the graph in 16.2. So according to Newton's second law, change in momentum over change in time is equal to the net force. So F delta T is equal to delta P. That is why it's the area under the graph. Let's move on to part C, where we are given that the diagram below shows one of the wheels of the car that is driven by the electric motor. And using Newton's third law, we have to explain how the frictional forces causes the car to accelerate. So as the frictional forces between the wheel and the road exert a backward force on the road will exert an equal amount of force forward on the wheel, causing it to accelerate. Part II. Calculate the resultant force acting on the car at t12 seconds using your answer to part AII. So we know F is equal to M times A. We know that the mass of the car is 1700, and the acceleration calculated was roughly about 1.6 meters per second, which gives me 2,720 newtons, or 2,700 newtons of force. For the next part, the black dot on the diagram represents the car at 12 seconds. The total resistive forces on car D are shown below. Calculate the constant total frictional force from the powered wheels which provide the thrust. Use your answer to draw an arrow on the diagram below to show that the direction and the magnitude of F. Okay, so net force is equal to the frictional force minus the drag force, okay, D. and therefore the frictional forces, the constant forces, will be equal to the net force plus the value of d, drag. Now, in the previous part, we calculated the resultant force to be 2,720, and the drag is 29,000. So 29,000, and that gives me 31,720 newtons, or rounded to two significant figures, it'll be 32 kilonewtons. So I'm going to work this out. I have to see how many divisions there are. So roughly from the point of start, so here to here, there are 26 divisions approximately. 26 divisions are 29 kilonewtons of force. So one division will be about 1.1 kilonewtons of force, and 32 newtons of force will be approximately 32 lines away, so roughly, and that is going to be my arrow, and that would represent 32 kilonewtons of force. Okay, let's move on to the next question. We've been given that an aircraft is flying horizontally at an altitude of 10,000 meters and a constant speed of 220 meters per second. While maintaining the speed, the controls are adjusted so that the aircraft is in projectile motion until the altitude of 7,500 meters. The passengers experience apparent weightlessness. Part AI, a condition for projectile motion is constant vertical acceleration. State another condition. There is constant horizontal velocity as well. Okay, for part II, show that the time taken to reach the new altitude of 7,500 meters is about 23 seconds. So let's look at what's going on. We've got an altitude of 10,000 meters, and the motion projectile, this is a horizontal projectile, so it goes to an altitude of 7,500 meters. We can use Suvat. Okay, we know the initial horizontal speed is 220 meters per second. S is equal to ut plus half a t squared. There's a drop of 10,000 minus 7,500, so it covers a distance of 2,500 meters. The initial velocity vertically is 0. So that gives half times a, which is 9.81, times t squared. So t is therefore 22.576 seconds, and that is 23 seconds to two significant figures. But we need to determine the magnitude and direction of the velocity of the aircraft at time t. It will have a magnitude direction like this. We would have to account for its horizontal velocity vx and vertical velocity vy. Vx is unchanged. Okay, there's constant horizontal velocity. So Vx is ux, which is 220 meters per second. But we do need to work out Vy. Okay, so Vy is equal, or V squared is equal to u squared plus 2as, and that is 0. So plus 2 times 9.81 times 2,500. And I'm just gonna, you can leave it as a unsquare rooted value, okay? Or I'm just gonna say it will be 15 root 218, so it's easier for me to square back in. And so the speed is going to be equal to Vx squared plus Vy squared all square rooted together, as it's the magnitude of the two components. And having put all those numbers, so 15 root 218 squared, that gives me a value of 312.17 meters per second, and that is, to two significant figures, 310. Then it's asking us to work out the angle to the vertical. So if we look at this diagram, we have Vx, we have Vy. It's asking us what would be this angle right here. That would be tan inverse of the Vx component over Vy component. Usually it's the other way around. Usually they ask for the angle to the horizontal. So watch out, it's not always to the horizontal. So with that, it would give me 44.8 degrees or 45 degrees. Okay, so that's part done. Let's move on. We have to explain why the engines of the aircraft must provide thrust during the projectile motion. Well, this is in order to maintain constant horizontal velocity. Otherwise, air resistance will reduce the horizontal velocity. Part BI. The average radius of the Earth is 6,400 kilometers. Show that the ratio is greater than 0.99. So the gravitational field strength at 10,000 altitude and that at the surface of the Earth, G, is inversely proportional to the ratio will be the radius at the surface, I'll call it the surface, divided by the radius of 10,000, which is going to be 10,000, or sorry, not 10,000, this will be 10 kilometers. I'll just leave it in kilometers, right? It's easier. So 10 kilometers plus 6,400 kilometers. So this is already 6,400. And just square it. That will give me 0.9969. For the next part, we explain why passengers are described as weightless during the projectile motion. That's because they are under free fall due to gravity. Therefore, they will experience no normal contact force with their chairs or seats. That's what weightlessness means. Question 18. Part of a machine to generate electrical energy using waves is a cylindrical drum whose cross-sectional is shown below. The height of the drum is 2 meters and its cross-sectional area is 0.79 meters squared. The mass of the drum is 1200 kilograms and the center of mass is 0.5 meters from one of the circular faces. The density of water is 1000. The drum floats in flat water with its long axis vertical. The base of the drum is a distance d below the surface, measured in meters. So we have to explain why the weight of water displaced must be equal to the weight of the drum. That's because upthrust is equal to the weight of the water displaced. Part II, we need to calculate the value of D. Because we know upthrust is equal to the weight of the water displaced, we would also, as we know that upthrust is rho GV and the weight is mg, G cancels out and I have the density of water. Now I need to think about the volume as I'm working out the value of D. So rho times volume is the cross-sectional area times the distance, and m as G cancels out. So D will be equal to m over rho times cross-sectional area, which is 1200 divided by 1000 times 0.79 meters squared, which gives me 1.52 meters. For the next part, it says upthrust forces act at the center of mass of the fluid displaced. Explain why the drum cannot float in equilibrium on its side with the long axis horizontal. So here we are, and what we are given now is that instead of this being in this position, now if we look at this position, okay, so bear in mind that the center of mass is, let's say, 0.5 over here meters. So now in this position, since the center of mass is where the weight acts from, and it's in a horizontal position, it would produce a net moment, okay, which would mean that it would no longer float, as there would be a net downward force acting on the drum. Let's move on to part B. When the vertical drum is displaced a distance x deeper into the water from the equilibrium position, the magnitude of the resultant force acting on the drum is now given by F equals minus kx, where k is a constant and d is measured in meters. By considering the magnitude of the additional upthrust on the drum, show that k is about 8,000 newtons per meter. We know upthrust equal rho gv, or a times, this time because it's been displaced a distance x deeper, and that is equal to kx. Okay, so that's equal to the force, resultant force, and x cancels out, and that would give me k as rho ga, where all values are provided to me in the question, the main question, and that gives me 7,749.9, which is, to one significant figure, 8,000 newtons per meter. So that is part I done. When the drum is released, it oscillates vertically. Explain why the oscillations are simple harmonic motion. Resultant force is directly proportional to negative displacement, my bad. And we also know that F, which is equal to ma, where m is constant, this would mean that A is also directly proportional to negative x. And this is one of the most important conditions where the acceleration is directly proportional to the displacement, but in the opposite direction. Okay, so let's move on to part where we need to calculate the natural frequency f of the oscillations. We have to think about omega, and we also know that f equals ma, f equals minus kx. Okay, so we know because these two are equal, then ma, which is equal to negative kx, and we know that a is equal to minus omega squared x. Okay, so the negatives and the x cancel each other out, and we get omega squared as k over m, and further we know that omega is 2 pi f squared. Omega squared is 2 pi f squared, or just simply put it as square root of k over m, and once you work out the frequency, you would have to divide by 2 pi, and you know the value of k, which was 7,749.9 over the mass, which is given to us as, I believe, 1,200. Let's just double check. Yep. So 1,200 right here, and that would give me a value of 0.41 Hertz. Let's move on. We're given two designs, A and B, of the machine, which are tested in a large ripple tank. The ripple tank can produce waves whose amplitude and frequency can be varied over wide ranges. The natural frequencies of the two machines are identical, and the graphs show the results but are incomplete. Describe how the amplitude of the machine could be measured at each frequency tested, complete the graphs with suitable labels and annotations, and discuss which of the designs is most effective at generating electrical energy. Let's talk about the graph's amplitude on the y-axis, frequency on the x-axis. Natural frequency is where resonance happens, as in resonance happens at when the natural frequency is equal to the applied frequency. So that's when it reaches the peak amplitude. So they have very similar natural frequencies, but clearly design A has a slightly higher natural frequency. So these values are F naughts. Let's talk about the amplitude measured at each frequency. Vary the driving frequencies using a signal generator. In terms of measuring the amplitude, I would use video analysis, where video is taken and a ruler is placed against, in this case, the drum, to calibrate the pixels to meters ratio, and then we can calculate the vertical distance from the still water level to the highest peak. I would consider taking a wide range of frequencies below and above this resonance state. So that's how I would get a range of amplitudes for each frequency. In terms of discussing the designs as to which one is more efficient at producing electrical energy, I would go for design B, because that design is more damped than A, as the resonance occurs at a lower natural frequency. I can tell that from the graph. This means basically that there is more energy available as electrical output, because more damping means less energy in the oscillations, and therefore more available to generate electrical energy. All right, let's move on to our next question. Number 19. So a lorry used to transport liquid oxygen has a tank with a maximum volume of 10 meters cube. The tank is filled until it contains 9.8 meters cube of liquid oxygen. And the pressure of the gas above the liquid is 100 kilopascals, and the temperature of the gas and the liquid is minus 183 degrees Celsius, the boiling point of oxygen. The temperature of the oxygen remains constant, and the walls of the tank allow thermal energy to pass through at a constant rate of 1.3 kilowatts. The latent heat of vaporization of oxygen is 214 kilojoules per kilogram, and the density of liquid oxygen is 1140. State why thermal energy passes into the tank. Because there is a temperature gradient. It's hotter outside, so there's a flow of energy from hot into cooler regions. Hence, it will pass into the tank. Part B. Explain why the temperature of oxygen remains constant despite the transfer of thermal energy into the tank. That is because potential energy increases and kinetic energy is constant. Thermal energy increases the internal energy, but potential energy increases instead of kinetic energy. That's why the temperature remains constant. Part C, show that in 1 hour, the volume of liquid oxygen that evaporates is about 0.02 meters cube. We are given the latent heat of vaporization, so E is equal to mLV, and we are working out the volume, so we have to involve mass as well as density, which is V will be equal to m over rho. I need to work out m, which is E over LV. I know energy is power times time. Stick in all the values. Power is 1.3 times 10 to the 3 watts times time 1 hour, 3,600 seconds. Latent heat is 214 hour. Didn't have to convert the units. Timesing by 1,000 was pointless, but that was gonna give me 21.869 ... And therefore V is equal to that value divided by the density 1,140. That gives me 0.019, roughly 0.02 meters cube. Part D, after 1 hour, the number of moles of gases above the remaining liquid is 710. Calculate the pressure. We know pressure is equal to nRT over V. N is 710, R is 8.31, T is minus 183 plus 273. Okay, so that will be 90 divided by the volume, which, bear in mind, is, so the total is 10, okay, maximum is 10, and it contains 9.8 meters cube of liquid oxygen, okay. So now that difference, okay, so 10 minus 9.8 meters cube, okay, that would be the remaining gas, plus we just worked out how much of that liquid oxygen had evaporated, which is 0.02. So that would be added on to this volume. So that is the volume up here. The answer, 2,410 kilopascals. So hope that makes sense. Okay, you gotta watch out for the volume of the gas, as it's talking about the gas above the remaining liquid oxygen. Let's move on to number 20. Question 20 says the specific heat capacities and molar masses of some common gases are given. We have to complete the missing value in the table to work out the number of particles per unit mass. It's just the Avogadro's constant divided by the mass. Avogadro's constant is 6.02 times 10 to the 23. Divided by the molar mass of krypton, which is 0.084, that will give me a value of 7.2 number of particles per unit mass, obviously times it by 10 to the 24, which is already included over here. Okay, so then we plot the missing data point and draw a line of best fit. There we are. Okay. For part C, we need to describe the relationship suggested by the graph and suggest an explanation. There is a linear relationship between specific heat capacity and the number of particles per unit mass. It's a straight line passing through the origin. And that means that for 1 kilogram, more particles means more particles will gain kinetic energy to raise the temperature by 1 Kelvin. Temperature rise corresponds to an increase in the average kinetic energy of the particles. So the energy required per kilogram per Kelvin is larger when there are more particles per kilogram. Okay, therefore larger specific heat capacity. Let's move on to question 21. Analysis of stellar light can identify the elements that are present in the outer layers of a star, absorption spectra of visible light from two main sequence stars, Vega and Tau Ceti, are shown. The spectra were collected by a telescope orbiting the Earth. The dark lines on the diagram show wavelengths where the intensity was 0 or close to 0. Explain the cause of these dark lines. Describe at least one difference between the spectra and analyze which star is older. Let's talk about the cause of the dark lines first. Okay, what happens is, let's say you have an atom, and this atom has two energy levels, hypothetically speaking. Okay, so an electron is sitting here. Now, when an incoming photon comes in and this electron absorbs this photon, it would be able to jump up. Now, depending on how much energy it absorbs, okay, which is equal to HF, and if that energy is equal to this E gap, okay, so the energy between the two energy levels, okay, then in that case, this electron will be able to get excited, jump up, i.e. And this missing wavelength or frequency would be registered as a dark line in a continuous spectrum. When these photons are re-emitted, the electrons get de-excited. Okay, so some of these electrons will get de-excited and they will jump down, and the photons will be re-emitted. Okay, these lines appear fainter as photons travel in random directions. So that's for the dark lines. When photons with HF equal to E gap, the energy levels of the atoms in the cooler gaseous layers, are absorbed by the electrons, they get excited and these missing wavelengths appear as dark lines. When these or other photons are re-emitted as electrons get de-excited, these lines appear to be fainter as these photons travel in random directions. Now, let's talk about differences in the two spectra. In Tau Ceti's spectra, there are more lines at different positions and also intensities, which indicate that there are more and different elements present. The lines which are different or not present in Vega's spectra are darker, affected by factors like temperature or pressures, external factors, and also the parts of re-emissions as we spoke earlier. So they can also affect the intensities. Those are some extra points, but you just have to mention one of them. In terms of the age, since Tau Ceti has heavier elements than hydrogen, as there are more lines, it's got to be older. Hydrogen takes millions of years to fuse into these elements, so Tau Ceti is the oldest star. Let's move on to the next question, number 22. An asteroid of mass 10 kilograms is in a circular orbit around the Sun at a distance of 3.5 AU from the center of the Sun, and use Kepler's third law to calculate the time period of this orbit in years. An object orbiting the Sun at a distance of 1 AU has a time period of 1 year. So, according to Kepler's third law, we know that T squared is proportional to R cubed. We use T equals R to the power of 3 over 2, where we don't have to convert anything because 1 AU has a time period of 1 year. So therefore 3.5 AU raised to the power of 3 over 2 will give me 6.55 years. So that will be my answer here. And for the next part, calculate the kinetic energy of the asteroid. Very simple again. Half mv squared is equal to kinetic energy, and we know it's a circular orbit, which means it's going to be 2 pi r over t whole squared. And if I just input the numbers, we have been given the mass as 10, and half times 10 times 2 pi r, 2 pi times radius 3.5 AU multiplied by the distance of 1.5 times 10 to the 11 meters divided by time period 6.55 times 365 days, 24 hours, 3600 seconds. So all that squared, and you would end up getting 1.3 times 10 to the 9 joules of energy. Okay, part B. It says after a collision, the asteroid falls towards the Sun. The graph shows the variation of Vg with the distance from the Sun. We have to use the graph to calculate the change in gravitational potential energy of the satellite from the collision until it crosses Earth's orbit at 1 AU from the Sun. At 3.5 AU, Vg is negative 0.25, and at 1 AU it is around minus 0.9. So the change in gravitational potential will be minus 0.9 minus 0.25. This is in gigajoules. The final answer should be in gigajoules. I would end up with minus 0.65 gigajoules per kilogram. And I know that the mass, for a mass of 10 kilos of the satellite, it would be therefore an answer of 6.5 gigajoules of energy. We can ignore the sign over here because it's just a change in gravitational potential energy. Next, the asteroid falls into a new orbit around the Sun, and this orbit is elliptical. State the other feature of this orbit predicted by Kepler's first law. According to Kepler's first law, the Sun is at one of the foci of the elliptical orbit. Question 23. The diagram shows the spectrum of light from galaxy M87 with a hydrogen alpha emission line. The spectrum of a sample of hydrogen gas analyzed in a lab on Earth showed this emission to be at 656.3 nanometers. Okay, and we've been given this graph, and we need to work out the magnitude of the recession velocity of M87. So we know that according to Doppler's effect, V over C is equal to change in lambda over the original. So we can rearrange this as V is lambda delta lambda over lambda times C, and delta lambda is the change in wavelength, 656.3, minus the peak average wavelength, which is 654 nanometers, divided by 656.3 times 3 times 10 to the 8 gives me 1050 kilometers per second. Part B. Estimate the distance in light years to M87 using Hubble's law. There's a correction. This should have been 10 to the minus 18. We know D is equal to V over H. Recession velocity was 1050 times 10 to the power of 3 to convert it into meters, and then divide this by Hubble's constant, and that would give me a value of 4.2 times 10 to the 23 get this in light years, where the conversion between meters and light years is to divide by 9.5 times 10 to the 15. This gives me 4.4 times 10 to the power of 7 light years. Okay, let's move on to our next question. We have to estimate the percentage uncertainty in the distance using the width of the emission line in the diagram. Let's look at the width. This value is 654.5, and this happens to be 653.5. So the width is therefore 1 nanometer. Okay, and so the percentage uncertainty is 1 over 656.3 minus the actual wavelength, the peak, which is 654. So 654.5 minus 653.5 and times that by 100. That gives me a value of 43%. According to the mark scheme, anything between 17 to 52% is allowed. Here's my range. Okay, so part D. Other methods have shown that M87 is actually 50 million light years from Earth. Suggest why M87 might contradict Hubble's law. This particular galaxy might be moving towards us, as its speed indicates blue shifted, unlike Hubble's law, which suggests galaxies are receding. Final part of this question asks us to suggest one reason why the Big Bang Theory is still acceptable as a model for the origin of the universe. CMBR supports it. That's the end of the paper. I hope you found this useful. See you in the next video. Thanks for watching.